Let's take a minute to talk about levers. A lever is one of our simple machines, and it operates, and how it works is that there is a fulcrum, a pivot point, and that is noted here with the red triangle. Okay, some examples that you might consider would be like a seesaw. If you can imagine a seesaw where a child sits on one end and another child sits on the other, and they teeter back and forth. Another one that I was very familiar with this past weekend was a shovel. I was trying to dig out a stump, and I was using the tip of the shovel, okay, was where the resistance was, trying to dig up underneath things, stumps, rocks, roots, that kind of stuff. And kind of the heel of the shovel acted as a fulcrum where it could pivot because the shovel had that shape. And then at the very end, the handle where I was putting my hands was where I applied the effort. And so I could pull down here, and as I was doing that, the tip of the shovel was trying to go up, but it was being stopped and pushed against by the resistance, whatever was underneath or on top of the shovel. You know, I got the shovel underneath a root and was trying to dig around it and dig up. And so I was trying to use leverage to dig up. Okay, I certainly wasn't strong enough just to reach down and use my hands and grab that, but I needed a long lever arm. Okay, so a lever also has mechanical advantage, and we've got ideal and actual, like the other simple machines. Okay, first we want to just point out that there are three different classes of levers. Okay, those classes of levers are based on where the fulcrum is. So a first class lever, you can see the fulcrum is somewhere in between the effort force and the resistance force. A second class lever, the fulcrum has shifted to the end. The effort is the furthest force from the fulcrum, and the resistance is closer. So another tool that I used was the wheelbarrow. As I dug up stuff and I needed to move it around the yard, I put the load inside the wheelbarrow. It pivoted at the end, right above the wheel there, basically at the wheel. And I would come to the opposite end from the wheel, and that's where I would grip the handles and pick up. I didn't have to lift as hard as, you know, how much load I had filled the wheelbarrow. I was getting a mechanical advantage here. And then a third class lever is where the fulcrum is still at the end, but notice the resistance is here on this end, and the effort is in the middle. And a good example here would be after, you know, reaching and messing with the wood and everything, is that I got a splinter, and I might have needed some tweezers. And so if you imagine another arm coming out here and the ends of the tweezers being a pivot point, okay, that would be your fulcrum there. Okay, and I would grip my tweezers this way, and the resistance, what I'm trying to grip with the tweezers, would be down here. So I'm applying the effort here, and there's some resistance of what I'm trying to grab. So this is a third class lever. Let's remind you that the ideal mechanical advantage formula is the effort distance divided by the distance of the resistance. If we point those out in these diagrams, you hopefully notice something. Now this fulcrum on a first class lever, it can slide anywhere between the two as long as those two stay at the end. So in this particular case, we're going to label DE right here, and DR is going to be right here. Now that fulcrum can shift to where DE or DR is bigger. It could even be right in the middle so that DE and DR are equal to each other. Okay, the mechanical advantage of this, it could be less than 1, it could be equal to 1 if it's right in the middle, and it could be greater than 1. So the mechanical advantage of a first class lever, where you get the advantage or the benefit, remember there's always that trade-off with forces and distances, benefit might be on the force, it might be on the distance side. It just depends on where you position that fulcrum. Okay? With a second class lever, okay, DE to the effort is always going to be longer than DR because the effort is always further from the fulcrum. So if DE is always bigger than DR, you always end up with a numerator greater than denominator. You'll always get a mechanical advantage greater than 1. So a second class lever is always going to give you a mechanical advantage bigger than one. And the third class lever, you can see that it's now the resistance that's furthest from the fulcrum. So dr is always going to be bigger, and your dE is going to be smaller, always, if it's a third class. So a dE smaller than a dr, you're going to have a fraction less than 1. Mechanical advantage here will always be less than 1. Now, one extra side note about these distances, just to be clear, make sure we're accurate. If you imagine, okay, a lever in the fulcrum, and you think about applying this effort force here, okay, the distance of the effort means as you apply this force, what is the path? How far does that effort, think of a hand, have to move or travel? Well, the path of travel would not be a straight line. This is, imagine that's connected so that the lever can't slide, but it just only can pivot. So the shape or the path that you're going to get is a circular path, right? And if the resistance could push hard enough and force this lever to rotate, again, it's a circular path. We notice that one is, this one would be clockwise, and the other is counterclockwise. Okay, so they're fighting against each other, which brings up another point we'll talk about in the next video. But the distance traveled is technically these distances that follow the path of a circle. And so you can see that what I've labeled is really from the fulcrum to where the effort is. And that would be, if you made a full circle, that would really just be the radius of a circle. But we always have to make sure we compare apples to apples. So, you know, the distances, the easy thing to say is if you know, with the force applied here, one revolution, you know, if we grab here and rotate the lever around one time, well, the other end would also rotate exactly one time. And so we could know that the distances to compare, just to figure out mechanical advantage, would be the circumference, you know, based on that radius and that radius. Well, circumference is pi times diameter. Also, diameter is 2 times r, right? So we have the diameter of the effort, this was the effort, okay, which really is just we could do double the radius. And then the resistance over here, we would do pi times its diameter. And then we end up with 2 times r, right, diameter. And so this is the radius of the resistance, and this is the radius of the effort. And I just want to show you that why am I only labeling these radii is that if I were to calculate the circumference, okay, of this circle and calculate the circumference of this circle, I used pi in both, and when we divide, we can cancel out common factors. So the pi's just cancel out. And then diameters, both are double a radius, so those common factors of 2 cancel out. And so really I was just reducing my fraction down from the very beginning just to get down to the radii. So the ratio of the radii is equivalent to the ratio of the circumferences, and the circumferences are technically these distances. Okay, those distances are technically circumferences.